Good afternoon, students. So yesterday we have seen the first unit, all the topics I have covered, all the definitions and everything we have seen. So today we are seeing about there is a second unit we are starting. It is about the groups we have. So from here, the main topic of the algebra will start. So that is about the groups definition. What are the conditions for a set to become a group? So those all topics we will cover in this unit. So here we'll see the definition of what is group, what is semi-group, what is abelian group. So like this, you will have the many definitions here, and if you know these concepts, with the help of this, you can find the, you can do the theorems, proof, and also if any problems are there, then you can do those problems with the help of them. Okay, now you are able to see the screen. So it is about the second unit we have. It is groups. Unit 2. So the main important topic of algebra. Okay. So here, so already in lower classes, that is in 10th standard and also even in intermediate, you have seen the conditions for any set of your either natural numbers or integers or real numbers or rational numbers or irrational numbers. So what are the conditions to become a group? Okay, so already these topics are there in your lower class here, but we are seeing some of the topics regarding of that one, and theorems are there. Okay, so with respect of real numbers, we have seen the additive properties and also multiplicative properties. Just if you know this concept, it is very useful for understanding the concept of the groups. Okay, so these, whatever the properties are there, you have studied in lower classes. The same properties will be useful here for doing the theorems. Okay, so set R of real numbers satisfy the following properties under addition and multiplication. Okay, so you are taking the set R of real numbers satisfy the following set R of real numbers satisfy the following properties under addition. Okay, for addition, this is the symbol we have. This is addition and dot, which we call it as a multiplication. Okay, so if you understand these properties, with the help of these properties, you can do whatever the groups theorems are there, or even rings theorems are there, that you can do. Okay, so first one with respect of addition, that is additive. Okay, first property we call it as A1. So this is called as a closure property. Okay, closure property. So closure property is that if you take A comma B belongs to capital R, then A plus B, that is with respect of what operation we are doing, that operation, that is if it is addition means plus operation, minus subtraction means minus operation, multiplication means dot operation, or division means whatever the symbol for division will be there, that operation, it will be closed under the set of real numbers here. So here A comma B if A comma B belongs to R implies A plus B, whatever the resultant you get, that also it belongs to R. Then we say that it is a closure property. Okay. So if you can take example 1 comma 2, if belongs to R implies 1 plus 2 equals to 3 also belongs to R. Okay. Like this, if you take any two numbers from the real numbers, if the addition of those numbers, whatever the resultant you're getting, that also belongs to R, then it is satisfying the closure property. Okay. Next one is A2. A2 is associative property. Associative property. Okay. Associative property means A into, that is A plus B plus C is equals to A plus B plus C for all A comma B comma C belongs to capital R. Okay. This is called as associative property. So if we take 1, 2, 3 as elements, 1 comma 2 comma 3 belongs to R, implies what will happen? 1 plus 2 plus 3 is equals to 1 plus 2 plus 3. So 1 plus 2 is 3, 3 plus 3 is equals to 6, 1 plus 5 is also 6. So it is satisfying the property of associative property. Okay. Next, if you see the third property, it is the identity property, A3. A3 is, we call it as additive identity or identity property. Okay. Identity property. So identity property means there exists an element 0. Okay. Then element 0 in R such that A plus 0 is equals to 0 plus A is equals to A. Okay. A plus 0 is A only. 0 plus A is also A. For all A belongs to R. Okay. So you can take the example. If 0 comma any element we have, that is A element you are taking 2 belongs to R, implies what will happen? 0 plus 2 is equals to 2 plus 0 is equals to 2. So it is satisfying the identity property here. Next, fourth property is A4. A4 is inverse property. Inverse property. So inverse property is with respect of addition and with respect of multiplication, the properties will be different. Okay, you have to remember that for each A belongs to R, there exists minus A belongs to R such that A plus minus A is equals to minus A plus A. So A plus minus A means what? It is 0. Okay. So minus A is called as the inverse of A. So this is the inverse property. You can take 2 comma minus 2. 2 comma minus 2 belongs to R. Then what will happen? So you can take here is above. If you take example here, it is minus 2 comma 2 if they belongs to R. Okay. So what will happen? 2 plus of minus 2 is equals to minus 2 plus 2 is equals to 0. Okay. Here whatever the identity element we have seen above, that we are getting in here the resultant. Okay. So minus 2 is the inverse of 2 here. Okay. Next, if you take A5, it is the commutative property. So commutative property is AB is equals to BA for all A comma B belongs to R. Okay. So if AB is equals to BA, then we call it as a, sorry, it is the addition, no? That is A plus B is equals to B plus A. A plus B is equals to B plus A for all A comma B belongs to R. So if we take the two elements, example, 1 comma 2 belongs to R implies 1 plus 2 is equals to 2 plus 1. Okay. So both are equal. So addition is commutative under addition in set of real numbers. Okay. So these are additive with respect to of addition. It is satisfying all the properties. So next, with respect to of multiplication, we will have properties. Same properties will be there. Just in place of plus, you will have the minus here. Sorry, that is a dot will be there. Dot or circle or star symbol will be there. These all most we will use for the multiplication. Sometimes they will mention in the question itself whether what it is representing, either addition or that is the multiplication. Okay. Next is the multiplicative operation. Multiplicative. That is a multiplication. Okay. We are taking here symbol dot. So same A1. A1 is the closure property. So closure property is, that is A comma B belongs to R implies AB belongs to R. Okay. Next to A2 is associative. That is A into BC is equals to AB into C. Okay. A into BC equals to AB into C for all A comma B comma C belongs to R. Okay. Next, A3 is identity. So identity property is that there exists one. So for multiplication, the identity element is 1 here. So 1 belongs to R such that 1 into A is equals to A into 1 is equals to A. So 1 into A is equals to A into 1 is equals to A for all A belongs to capital R. Okay. This is the identity property. Next, A4 we have inverse property. So inverse property is for each A not equals to 0 belongs to R. So whatever A is there, that value is not equals to 0, which belongs to real numbers. There exists A inverse belongs to R. There exists A inverse belongs to R such that A into A inverse is equals to A inverse into A is equals to 1. Okay. This is the inverse property. A inverse into A is equals to 1. Okay. So just a slight difference will be there with respect to of addition and also multiplication. A into A inverse is equals to, so you can take here example for all this somewhat easy will be the examples. If you take for inverse here, you can take example if 2 belongs to 2 comma 2 inverse belongs to R. Then how you can write 2 into 2 inverse is equals to 2 inverse into 2 is equals to 1. 2 inverse and means either with the help of the logarithm we can do, or with the help of 2 into 2 inverse means 1 by 2. If you cancel both, you will get as 1. Okay. So this inverse means 1 by 2. It is a fraction. So it belongs to the real numbers. Okay. After A4, we have A5 commutative property. So commutative property is AB is equals to BA for all A comma B belongs to R. Okay. Next we have D1 property. So in multiplication, one more property will be there. That property is distributive property. So distributive property will be there. The distributive property is A into B plus C is equals to AB plus AC for all A comma B comma C belongs to R. Okay. This is the property called as a distributive property. So like this, if any set satisfy these all properties with respect to of addition and also with respect to of multiplication. Okay. So if you know with respect to of addition, what is identity element and also inverse, and also with respect to of multiplication, identity element and also inverse, easily you can do the theorems and also problems here. Okay. Next we'll go into the unit, that is the unit 2. In this we have first definition about the what is binary operation. So binary operation means whatever the operations we are just now we have seen, that is we have seen addition and also we have seen the dot as a multiplication. So some more symbols will be there which we are whatever the symbols we are using for solving the theorems and also problems, those symbols are called as a binary operations. So okay, let S be a non-empty set, a mapping of function S into S to, that is S cross S to S is called a binary operation on S. Okay. How we have the binary operations? Means they are denoted by the symbols. Some symbols are there. So usually these symbols we'll use for representation of addition and also multiplication. So first we have the concept of what is binary operation. Binary operation. So binary operation means let S be a non-empty set. Let S be a non-empty set, a mapping of F S cross S to S. Okay, a mapping of F S cross S to S is called a binary operation. Is called a binary operation. On S. So here we are taking S as a set. Therefore, on set S, it is called as a binary operation. So denoted by symbols. So like the symbols are here, plus multiplication dot will be there, or like this star will be there, or like this circle. Okay. So these usually will take as a binary operations. Okay. Next we have that main important one, representation for a group, that is the algebraic structure is there. algebraic structure. So algebraic structure means representation of any set and any one operation. Combination of these two is called as a algebraic structure. Okay. A non-empty set G equipped with equipped in the sense it is combined with equipped with a binary operation is called an algebraic structure. Okay. Is called algebraic structure, or we call it as algebraic system. Okay. Anything equipped with a binary operation is called an algebraic structure or algebraic system. Okay. So example we will write like this, that is n comma plus n comma dot or z comma plus or z comma dot or q comma plus q comma dot. Next r comma plus comma r comma dot. Okay. These are natural numbers, integers, rational numbers, and real numbers. Okay. Any even complex number also, c comma plus c comma dot or q complement comma plus or q complement comma dot, that is a irrational numbers. So like this, representation of any non-empty set with any binary operation is called as an algebraic structure or algebraic system. Next we have the concept of a groupoid. Groupoid in the sense a non-empty set G equipped with one binary operation star is called groupoid. So with any one binary operation, a non-empty set, if it is equipped with that one, it is called as a, that is groupoid means it is satisfying the condition of addition or multiplication with respect to of those set. So that is called as a groupoid. So next we have the concept of semi-group. This is the main important one. Semi-group, if you means one definitions will be there to know the definition of what is group. Okay. Semi-group is semi-group means an algebraic structure S comma dot is called a semi-group if the binary operation satisfies associative property. Okay. If any set of non-empty set, if it is satisfying the associative property, then that set is called as a, means it is whatever the algebraic structure is there, that algebraic structure is a semi-group. Okay. So an algebraic structure S comma dot is called a semi-group, is called a semi-group if the binary operation, here whatever the operation is there, that if the binary operation satisfies associative property. Okay, that is, what is associative property? Just now I have to know. That is A into B into C is equals to A into B into C. Okay. So with respect to of dot here, we are using that operation. If it is satisfied this one, then it is called as a semi-group. A comma B comma C belongs to yes. Okay. So here, so some of the algebraic structures are there which are satisfying the, which become the semi-group, and some algebraic structures are there which do not become the semi-group. Okay, you can take the example here. So the algebraic structures, so here n comma plus associative property with respect to of natural numbers, integers with respect to of additions, integers with respect to of multiplications. Okay, z comma into, next we have rational numbers with respect to of multiplication or semi groups. Okay, so you can take even real numbers also. So the sum we are taking the example here. Natural numbers with respect to of addition, integers with respect to of addition, and also multiplication and ratio. These are the rational numbers. Okay. But here, but z comma minus is not a semi-group. Able to see, no? So is not a semi-group because subtraction is not commutative. Because subtraction is not commutative. Sorry, not associative. So subtraction is not associative. Therefore, with respect to of subtraction, it is not a semi-group. You can check them with the help of example also. So if you take any three numbers and if you apply the associative property with respect to of subtraction, then we see that associative property is not satisfied with the subtraction. Next one is the monoid is there. Monoid means a semi-group is called a monoid if there exists an identity element E in S such that, means if whatever the semi-group is there, if that semi-group is satisfying the identity property, then when we call that group as a semi-group. Okay. Monoid. Okay. Monoid in the sense if it satisfies the identity property. A semi-group is called monoid is called monoid is called monoid if there exists an identity, if there exists an identity element E in S such that E into A is equals to A into E is equals to E. E is the identity element, no? So A, okay. Here E is the identity element. It depends on the binary operation. If it is a plus, okay, then you will have the symbol here plus and also here 0 will be there. If it's the multiplication means identity element will be 1. So 1 into A into 1 is equals to A for all A belongs to S. Okay. So a semi-group is called a monoid if there exists an identity element E in S such that E into A into E equals to A. Okay. This is the monoid definition we have. Next example for the semi group, that is example for the monoid is that it should satisfy the associative property, and also it has to satisfy the identity properties. Okay. So the semi-group n comma multiplication is a monoid because one is the identity for the multiplication. But the semi-group n comma plus is not monoid. Okay. Because 0 is the identity for addition, which is not in natural numbers. You can take here examples. N comma plus the semi-group in the sense it is satisfying the associative property. The semi-group n comma into, okay, n comma into means natural numbers with respect of multiplication is a monoid, because one is the identity, element for the multiplication. One is the identity for the multiplication. Okay. So one will be there in the natural numbers, but semi-group n comma plus is not a monoid because 0 is the identity for because 0 is the identity for addition, which is not in natural numbers. In natural numbers, 0 will be not there. Therefore, with respect to your addition, natural numbers will not become the monoid. 0 is the identity for addition, which is not in natural numbers. Okay. So these two are the examples. So you can tell that is natural numbers with respect to of multiplication is a monoid, but with respect to of addition, it is not a monoid. Okay. So other examples which we with respect to of addition and also with respect to of multiplication, both they are that is monoid is the matrices we have now. Matrices is the best example here we can see. So that is m comma plus and m comma into are monoid. So m is for this is the matrices. Okay. So here if you take the 0 matrix 0 0 0 0 plus 1 2 3 4. So that is 0 plus a if you think. What we will get? 1 2 3 4. That is 0 plus a is equals to a. So it is satisfying the identity property here. And also if we take the identity matrix 1 0 0 1 and multiplication of 1 2 3 4, you will get 1 2 3 4. That is 1 into a is equals to a you are getting. So with respect to of multiplication and with respect to of addition, matrices we are satisfying the conditions of the monoid. Therefore, matrices with respect to of addition and multiplication, it is a monoid. Okay. So this is the main thing with respect to of addition and also with respect to of multiplication. So just now we have seen the definition of what is semi-group, what is monoid. Okay, so one more definition we have that is the for inverse. So inverse property just now I have told no with respect to of addition and also multiplication. Okay, next, what is the inverse of the whatever the element is there? For that, how to find the inverse means there is, let S comma dot be a monoid. Okay, monoid means it is satisfying associative property and also it is satisfying the identity property. Okay, monoid and EB its identity, EB its identity element, EB its identity element. Let A belongs to S. If B belongs to S, okay, B is another element. If it belongs to S, B such that A dot B is equals to B dot A is equals to E. Okay, A dot B equals to B dot A is equals to E. Okay, you can write like this or else like this also you can write E in the middle and here B dot A. Same, both will be same. Okay, then B is called an inverse of A. Okay, an inverse of A. This is the definition of the inverse property, whatever we have. Okay, S comma dot be a monoid and E be its identity element. Let A belongs to S. If B also belongs to S, such that A dot B is equals to E equals to B dot E. That is, just before I have told, no, A into A inverse equals to 1 equals to A inverse into A. Same that property. Here we are taking A and B as the two elements. Okay. So the best example for this one, which is satisfying the inverse property, is Z comma plus. Okay. Z comma plus is a monoid in which every element is invertible, means it satisfies the inverse property. Every element is invertible. So in which every element is invertible. Okay. So you can tell like this: if A belongs to Z, we have minus A belongs to Z, such that A plus minus A is equals to 0, minus A plus A. Okay. So A plus minus A equals to 0 equals to minus A plus A. It is satisfying the property, that is inverse property with respect of addition, and hence minus A is an inverse of A in integer Z. Okay. And second example is in the monoid Z comma dot. Okay, Z comma dot 1 and minus 1. That means with respect of multiplication. 1 and minus 1 are the only invertible elements. 1 and -1 are the only invertible elements. Okay. With respect of multiplication, these two are the invertible elements. Third one, in the monoid, r comma dot, that is real numbers with respect of multiplication. All the elements except 0 are invertible. So except 0, all the elements will have that, all the elements will satisfy the inverse property. Okay. This is about the inverse property. So first one we have seen about the semi-group. Next one is the monoid we have seen. Next we have the inverse property. Now the main thing is about what is the definition of a group. Okay. So the group definition is that the algebraic structure G comma dot is called a group of if G is a non-empty set and dot is a binary operation on G satisfying the following properties. Okay. If it is satisfying these all properties, then we call whatever the algebraic structure is there, that algebraic structure is a group. Okay. So main whatever the heading we have group, that we have here definition. Okay. Group. The algebraic structure G comma dot, okay, G comma dot is called a group if G is a non-empty set, if G is non-empty set, and here whatever dot is there, dot is binary operation on S, sorry, on G, your set is G, no? On G satisfying the following properties. Satisfying the following properties. Okay. So what are those properties means? Just now we have seen closure property, associative property, identity property, inverse property, and also commutative property. Like that, whatever the properties are there. So if the algebraic structure is satisfying those properties, then we call it as a group. First one is G1, that is a closure. Okay. Closure is what we have A belongs to G, comma B belongs to G implies here we are taking the operation as A dot B, no, A dot B belongs to G. Okay. So this is the closure property. Next, second one, G2 is associative. That is A into B into C is equals to A into B into C. Okay. A into B into C is equals to A into B into C. For all A comma B comma C belongs to G. This is the associative property. Next, G3 is identity. That will tell as the existence of identity. There exists an element E in G there exists an element E. E is the identity element. So E in G such that A into E is equals to A is equals to E into A. For all A belongs to G. Okay. This is the identity property. Okay. Here E is the identity element. So this is the third property. Next, fourth one is inverse. That is called as G4. So inverse property is, that is, for each element A, for each element A in G, there exists an element B in G such that A dot B is equals to E is equals to B dot A. Then what we call B is inverse of A. Okay. So B is called as the inverse of A. If any algebraic structure is satisfying these four properties, then we call that algebraic structure is a group. Okay. Or in shortcut, we can tell that a monoid in which every element is invertible is called a group. Okay. So one note we have, in shortcut, we can tell that a monoid in which every element is invertible is called a group. Okay, that means monoid means we have the associative property and identity property. If with respect to of addition, associative and identity, if it is satisfying even inverse property, then we call it as a group. Okay. So now you can take the example of what are groups, which set of algebraic structures are there. They are satisfying these four conditions. That is Z comma plus Q comma plus R comma plus and C comma plus. That is complex numbers. Okay, these are groups. And which are not groups, okay, that are N comma plus, that is natural numbers with respect to of addition, natural numbers with respect to of multiplication, Z with respect to of multiplication, are not groups. Okay. So these are the examples of algebraic structures which are groups and which are not groups. Okay. Next we have what is abelian group, or we call it as a commutative group. Commutative group or abelian group. So on this you will have theorems. Abelian group and also we call it as a commutative group. So just now we have seen the properties. No, a group, if it satisfies the commutative property, then we call it as a abelian group. That means it has to satisfy all the G5 up to G1, G2, G4 group properties and also additional one commutative property. Then we call it as a abelian group. Okay. abelian group. A group G comma dot is called an abelian group if the binary operation dot whatever it is there dot satisfies the commutative property. Okay, that is commutative property is A dot B is equals to B dot A for all A comma B belongs to G. Okay, you can take this as a G5 property. Example here. So Z comma plus R comma plus and Q comma plus are examples of the abelian group. Okay, so a group G comma dot is called an abelian group if the binary operation dot satisfies the commutative property. What is the commutative property? A into B is equals to B into A. So for all A comma B belongs to G. So next we have what is a finite group and also what is infinite group. A group G comma dot is said to be a finite group if its underlying set G is a finite set. And a group which is not a finite set, it is called as an infinite group. Means the elements whatever are there in the particular set, if it is having the finite number of elements, it is called as a finite group. If it is having the infinite number of elements, then we call it as a infinite group. Okay. Finite and infinite group. Finite and infinite group. Okay. A group G comma dot is said to be finite if its underlying set G is a finite set. Okay. And a group which is not finite, is called an infinite group. Okay. So this is the definition of finite and infinite group. Next one important one is there. On this also you will have the theorem, that is the order of a group. So how we will find the order of a group? That is the number of elements in a finite group is called the order of the group, denoted by that is we will write O of G. Okay, this is the representation of order of a group. If G comma dot is an infinite group, then it is said to be an infinite order. So if it is an infinite group, it will have infinite order. Order of a group. So order of a group means the number of elements the number of elements in a finite group is called the order of the group. Okay, denoted by order of G, like this. Okay, if G comma dot, if G comma dot is an infinite group, then it is said to be, then it is said to be of infinite order. Okay, these are the main important, whatever the definitions are there in the textbook for solving the problems and also theorems. So you should know what is a group, what is a semi-group, what is a monoid, and what is an abelian group. Okay. Next, in set unit 1, I have told the addition modulo and also multiplication modulo, I have told, no. So from that addition and multiplication modulo, whatever the concepts we have seen there, so you have one problem. So whatever the set is there, set will be given. You have to show that whether it is an means it is becoming the abelian group or group with respect to of multiplication modulo, either multiplication modulo or addition modulo with respect to of whatever the number given in the textbook. Okay. So in this, the theorems are on the group and also abelian group. Some theorems are there that you can see in the textbook and you can practice them. So definitions, almost I have told all the definitions here. Group definition we have seen. Abelian group we have seen. And one problem we have on, that is addition modulo and multiplication modulo. Next, after that we have elementary properties of a group. So in this we have cancellation laws are there. Left cancellation law and also right cancellation law will be there. And showing that set S comma dot is a finite semigroup in which both the cancellation laws hold. Then S comma dot is a group. So whatever these theorems are there, try to practice these all theorems. 2.3.3 theorem and also 2.3.5 theorem. Next, we have worked out exercise. In that, some problems are there and also some theorems are there. Proof. You have to see them. Okay. And 2.4.5 theorem is the for 10 marks question you will get in the examination. So G comma dot is an abelian group you have to show, means that is whatever the property, commutative property is there. If you show that, then from that you can tell that it is a abelian group. Next we have finite groups. 2.5. Just now I have told the definition. No? On that, you have the theorems are there. So by that we'll complete the unit 2. So next class we'll go to the unit 3 subgroups and also cyclic groups. Okay. So one problem on addition modulo and multiplication modulo we'll see in the next class.